So our first talk of the afternoon session is going to be given by Katie Broad, using Shackleton Crater as a case study for pairing ground-based and satellite gravimetry to investigate the subsurface structure of impact craters. Take it away.
Thank you. Sorry about the mouthful there. Okay, yeah, I'm Katie Broad, and I will not repeat the very long title that Cassie just said. Thank you, Cassie. All right, so the overall kind of overarching theme of what I'm looking into is target properties and how they affect impact crater formation. So here, this is a very broad sweeping generalization, and you can see the scale bars. There's 1 centimeter and 4 millimeter. This is just like an experiment that shows where shock energy travels in different porosity of media. Anyway, so we see that a medium with no porosity tends to take on fracturing, take on porosity. That shock energy is usually expended via fracturing. And in a porous medium like sandstone, which has 23% porosity in this experiment, it tends to get compacted and more dense post the impact, that structure. So another piece of background is what the residual Bouguer anomaly is. Basically, it's used to describe the bulk density structure of an impact crater. We're looking at basically the gravity inside versus the gravity outside of a crater. So a negative residual Bouguer anomaly would be the inside gravity is less than the outside gravity. So the inside less dense than the outside, porous interior, right? Or fractured, whatever you want to call it. Then the positive RBA would be the opposite. So the inside gravity would be more strong than the outside gravity. It would have a more dense interior. And connecting that with the previous slide, so porous crust, I'm saying crust because now we're starting to get into the generalized planetary stuff. Porous crust tends to have dense craters and therefore a positive RBA, more gravity inside than outside. And then a dense crust tends to produce porous craters relatively and produce a negative RBA. You can see in this model, basically they modeled different final crater porosities in different media. The green and the red are like have porosity. Sorry, they have porosity. And this blue line is 0% porosity. So you can see that's very obviously negative residual Bouguer anomalies for non-porous media and positive trending towards that for more porous media. Applying this to the moon, GRAIL, which is the Gravity Recovery and Interior Laboratory, I believe, took a bunch of gravity data on the moon. And those residual Bouguer anomaly measurements actually reflect the fact that the regional crustal porosity correlates to observed RBA values. I said the caveat right at the beginning that this is very broad sweeping because as you can see, there's a lot of wiggle room here. But in general, the trend holds up and there's very clear relationship between target porosity and final crater porosity, density structure, that kind of thing. So looking farther into the RBAs we've gotten from GRAIL on the moon, as crater excavation depth increases, the RBA trends change, which implies potentially a layered subsurface. So on the left here, we have a paper by Cristal Izquierdo. She basically did a whole survey of all these tiny craters on the moon and took their residual Bouguer anomaly value and plotted them up. And she found, you can see why no one had done this before. This is a lot of work. She found a discontinuity at a certain crater diameter. And so as you increase your crater diameter, you increase the excavation depth, the crater disrupts deeper material and interacts with deeper material. So Cristal interpreted that discontinuity as a discontinuity in subsurface porosity, which on the top left, you can see kind of a very generalized schematic of how that would look. So it would be discrete layers, which would be regolith, megaregolith layers. And that discontinuity she identifies at about 3 to 5 kilometer depth is when that porosity starts decreasing significantly. Over here on the right, I have just a continuing crater diameter size and RBA values. So we see that downward trend continue and then kind of level off. And I didn't double check this, but it's probably because it reaches down to like the mantle through the crust. And it kind of is the same regardless.
Those also correspond with morphology changes. So
yeah.
First one is a simple to complex transition. And then
Yes. So actually, I remember, so Crystal came to Baylor and gave a talk about this. And I asked her, I was like, this kind of corresponds to a simple to complex transition. And I thought of this like right before I talk, and I was like, someone might ask about that. She gave a very convincing answer as to why it's not necessarily that transition that is determinant of those that discontinuity.
So it's a coincidence.
It is a coincidence. There might be something deeper in like causation wise, but she convinced me thoroughly that this is not necessarily a simple to complex transition, because I was also skeptical for sure. But I can get back to you on that. I can look that back up. Okay, so we can see this beautiful gravity map from Grail. It has provided one of the most complete, if not the most complete gravity map of any planetary body in our solar system. Why am I still harping on gravity? Why do we still need more of it? Why am I so greedy? So basically the resolution of Grail spatially is about 13 kilometers as far as getting like residual Bouguer anomaly data and that kind of thing. So it makes it insufficient to be probing much shallower than that 3 to 5 kilometer discontinuity supposedly. That's just around that limit where we can't really diagnose. And I will go back here. It starts to get really, really fuzzy the shallower you get. So am I like, sorry for the people online, if I'm stepping away from the microphone and coming back, my volume might be really inconsistent. Okay.
So let me double check that. Okay, the video should be still going, and so they should also be able to see it, which helps with the pointing.
Okay, yeah, I try to say left and right and all that stuff, but I don't always. Okay. So yeah, okay. The resolution of Grail isn't high enough where we can probe the subsurface, and it starts getting really fuzzy as surface properties start becoming a lot more, like surface property changes start becoming much more localized, like those trends. So we can't necessarily do global comparisons anymore at that scale. So instead of launching a brand new Grail mission that has a bunch more resolution and that kind of thing, we're proposing that surface gravity measurements would actually be more fruitful. Well, actually, this is from Apollo 17. This is the only gravity traverse that has been done on the surface of the moon. And I think it's really, really cool. I talked to Jack Schmidt, who was one of the people that deployed it. But yeah, so it has been done before. It is possible. We have done it. And I think we should do it more. And I'll tell you why. So Grail gravity interpretations, or really gravity in general, is inherently non-unique. The gravity signal is based on the bulk density of what's beneath it, has no way to distinguish like structures and such. So these 4 different cases are all plausible interpretations of the Grail signal at Shackleton crater, which I'll talk more about later. But yeah, so the case A is uniform density. It's what a lot of people will use, you know, first order gravity analysis for general reasons, but that's not very practical of a subsurface structure. It's not likely that the entire subsurface of the moon is uniform porosity wise. So we have case B, which is a low density breccia lens, which I think is similar to what Marley was presenting on earlier, where it has a lot of breccia infill and a lot of regolith and boulders and such, making it really low density. We have low density megaregolith, which I would think would be more alike for newer craters, which has that fresh excavation and a lot of eject on the outside, and also a kind of constant gradation of density. With depth, that's case D, that likely be a more evolved older crater structure. But at this point, any of these could be true based on our measurements at Shackleton Crater. And each of these types of scenarios has different implications for how impact processes occur, what the moon's subsurface looks like, and even our understanding of impact craters and other planetary bodies. So it's important to distinguish these things. As far as surface gravimetry goes, this is a very crude diagram, but gravity at the surface is sensitive, I would say. Just this is my personal opinion vibes. Basically, it's most sensitive to shallow things like 1 to 2 kilometers depth. And so on the left here, you can see a flat kind of, what's the word I'm looking for? Flat discontinuity of density that is represented by that case C in this previous slide. And you can see as you traverse that topography, if your topography changes, you get a different signal versus a scenario like scenario D, I believe. Yes, D, which has that constant density degradation. You wouldn't get as much change in your gravity signal as you go up and down the topography. So you would get different signals based on different subsurface structures. And what we're doing is we are basically proposing to supplement the GRAIL data with ground-based gravimetry to constrain possible substructures. So GRAIL, we get these possible substructures, things that could be, and then we can distinguish between those things using that ground-based gravity. Just to drive it home, we're combining the two. Okay, so the upcoming Artemis missions are going to the South Pole Aitken Basin. And the South Pole, okay, SPA. SPA is the oldest confirmed impact on the moon at the moment, and it is full of very interesting things. It's at the lunar South Pole, which is an interesting place in and of itself. It has it will provide lots of interesting information as far as lunar crustal history, thermal history, and even like solar system bombardment history, that kind of thing. Yeah, okay, that's all I have to say on that. For our specific case study, we utilized a portion of a proposed Artemis 3 traverse along the Shackleton de Gerlache Ridge, which is why I was showing Shackleton earlier, is that's related to what we're doing here. So I have on the top right this visual of where Shackleton is in relation to other parts of the moon. So the near side is over here. It's right at the South Pole. That star is the South Pole, and the Shackleton de Gerlache Ridge is circled by that yellow circle. So we're using the PSR1 to SR1. It's kind of better shown here on a DEM I made in MATLAB. Yeah, basically what we're doing based on the contoured DEM, we're basically going uphill closer to that crater. So we're experiencing a lot of topographic variation, which will help us distinguish that much more what's going on under the surface. So believe it or not, this took the longest out of this whole project. Just splitting up a DEM into squares, believe it or not. So it's really complex to be making these topographic corrections to gravity measurements at the surface because topography is complex. So our model wants to know, if I put a gravimeter here, what is the gravity going to look like based on the stuff around me? And so we split all the topography around you into finite prisms, discretized prisms, because the gravity from a prism is finite and calculable. And I can make a code for that. So basically my code splits DEM into prisms that it gets smaller the closer you get to the gravity measurement, because very far away, the gravity values are very small and they can be kind of averaged out over a large surface. So that's why here is okay, even though there's so much topographic difference. Okay, so here are our results so far. What we see is that the Bouguer signals from the traverse would actually produce significantly different measurements. So we have all 4 cases that I showed earlier. Case A being this, where it basically doesn't change along your whole traverse. And you can see these values are more than a milligal apart. C and D are pretty similar, but a lot of areas in that traverse have about a milligal of difference. And most commercial gravimeters on the market have a microgal precision. So those are very easily resolvable, even with potentially lower resolution on the moon with a more robust instrument, perhaps. Yeah, so we can actually resolve some of these differences between these subsurface structures. And all you have to do is carry a little guy with you while you walk on the moon. You don't have to dig, you don't have to plant something there for a long period of time. You just take a measurement. The gravimeters on the market take about a minute to do one measurement. So either way. So next we will be utilizing that Apollo 17 gravity data that I talked about earlier. And so basically we're putting our model to the test. So on the left, we have a model that was done purely using the ground-based gravity traverse on Apollo 17. This model has a thin layer of dense basalt just under the surface. This is technically a solution that is viable with the gravity that they collected. But looking at Apollo 17 seismic data, this is also a viable solution to the subsurface structure, which is like a more gradated density structure with low density stuff at the surface and much denser stuff towards the bottom. So clearly there is, it's open to interpretation what the exact substructure of this looks like. So our model, these are the actual gravity data from the traverse. This is heavily adapted from the previous slide, but it was a good picture, so I took it. So this is an example of what we'd put into our model, that more gradated density structure. We would model what the gravity would look like at each of these points, given this subsurface structure. And we would do different subsurface structure scenarios and see which one fits best, combining Grail data, constraining what it would look like underneath Grail data versus, and then adding the model data from a ground-based traverse. So in summary, we have our results are that ground-based gravity measurements would distinguish between paradigms that cannot be resolved by Grail. And I'm open for questions. I think I didn't hit very well. What's my time on that?
I think we have about 10 minutes left. So we have questions in the room.
Please, open to ideas.
Looks like maybe Sierra has a question to start.
Hey, Katie, great talk. My question is how would your results change depending on the DEM used? Because I wasn't clear if this
That
was
is
like
kind
low
of-
derived topography or like from LRock or.
Yeah, so this DEM we have right here is 5-meter resolution. And could you repeat your question so I'm answering it concisely? Sorry.
So if your DEM, for example, came from LOLA data versus LRock NAC imagery, how does that affect your results?
I'm not sure because I don't know totally the difference between what the data quality and what that would look like between the two. Obviously lower resolution data sets would give less accurate models. But yes, does that answer your question? Do you need more? Sorry.
Yeah.
Okay, yeah, this is very generalized, so I think it would be applicable to a lot of different types of data sets. It just depends on how fine you need your topographic model to be. If you have not that much topography going on around you, you can have a much coarser data set and be fine. But here the topography is highly variable, so a higher resolution data set is more ideal. So yeah. Any other question?
I see what you were pointing towards with the breccia.
Yes,
lens.
yeah.
Really cool.
Thank you.
One question I have is, and like we're talking, like this is Shackleton, it's pretty big, it's probably
Yeah.
like rock.
Yeah.
But like for thinking about smaller craters, like is it possible to auto brecciate your rocks if there are no rocks there? Can you make a rock out of nothing?
If I knew more about rock mechanics, I would know. But I would assume, again, we'll go back to the little tiny 2 centimeter uh experiment here, but like I'm assuming that fracturing can create those like big fractured boulders and super
Right, you
variable
probably need
precious
something
items.
there,
Probably.
right?
Yeah. I don't know how. I know that fracturing would go beneath the ground. I don't know how that would translate to expelled material. If that would expel more boulders versus a lower density media, because that has. Let me see the key.
Yeah, if I could add one thing there, I think one other thing is possible is that the basically impact melt is derived from these, gets injected into the cracks, and that can create rocks too. So you got the melt pool, and then the breccia ejected and the melt ejected in the cracks.
Yes, yeah, that's a good point.
Interesting.
You can probably create a bunch of boulders and chunks of things, but I don't know how you define rocks.
So there's another question online. Sasha asked, are you using P4ST or Clawpack to do the modeling?
Ooh, I made my own model. I made a code that automatically breaks up a DE squares, and then I made a code that calculates the gravity from the what's the quadrilateral prism or something. Yeah, and it adds it all up. I think there were codes that kind of did this already. But I guess I have control issues and I made it myself. Yeah.
I was wondering about the okay, wait, there was a slide you had where it was showing like the potential, like that first order, yeah, you were just
Here?
showing- Yeah,
Mhm.
like what it potentially could be
Mhm.
based off the data that we have.
Mhm.
You might have mentioned it, but based off that data, like, is there any, besides all four of those, is there any one that would be particularly likely?
We don't have like the surface data right now, but just like gut feeling, I think it will be kind of probably either a mix between these two or a mix between these two, depending on what kind of surface processes have occurred on the South Pole specifically. But these are different enough where I think we would be able to distinguish kind of, it might be a little bit of this, it might be a little bit of this and that kind of thing. But I would lean more towards C and D, if not more C. Because I think C is what the Cristalli-Hierro paper was kind of implying, that like discrete layers of density earlier. Yeah, that was a long-winded answer.
Would we expect D to happen? Like, under what circumstances do you get that type of layering?
Yeah.
That's like this.
Yeah, so I think it would be very like old craters that would have sufficiently like, I think, I don't want to use the term wrong, but impact gardening and that kind of thing that would have over long enough periods of time that subsurface starts to kind of get uniform. Does that make sense?
Yeah, the walls of Shackleton are super steep. They're like the steep.
Yeah, so yeah, you're right. I don't necessarily expect this all the way down here to be what Shackleton says. But yeah, I think this would make more sense for much smaller craters than Shackleton. But technically, this is a viable solution to the gravity data, which is another support for we need more than just that.
So this is kind of a question going back to several of your questions for Marley's talk, right? Which is, are there other observations that we might be able to make without doing the gravity traverse that might also be able to distinguish between some of the different density profiles?
Yeah, so we can do seismic studies. Those take a lot longer and require, us to put something on the ground, but that's similar to the work you would have to do for a gravity data set, but the gravity traverse would also get more like spatial differences versus a seismic experiment. You might, I know there have been proposals for like a network, like a line of seismometers, and it's just really hard to do seismic stuff on the moon. I know the Lunar Seismic Network is supposed to, is hopefully going to come to fruition sometime soon, but what was I trying to thought? Yes, so seismic possibility, still more difficult than gravity, I would say. It has higher resolution and it could be more fruitful for finer resolution things. But gravity is a good broad strokes way to get there. Also GPR gets that top like 5 to 10 meters depending on the material itself. But again, that's very dependent on the material. So I believe Chang'e 3 had a GPR, and there was a study that came out recently that characterized that top. I think they got down to 6 meters of the lunar subsurface, but gravity, it's that fuzzy difference between here, back here, here, between 10 meters and 3 kilometers, but like we can't quite get to. Seismic stuff would be great, but localized regions are harder to get. We can't necessarily put a seismometer every single place we go, potentially. Yes, I have it.
Okay, this is kind of building on my last question. So apologies if the answer is similar, but how would any of the uncertainties in the elevation, so say it's like 5 meters plus or minus 2 meters or something, how do those uncertainties in the topography play into your data and the interpretations?
That, yes, that would play into it for sure. Hopefully we would get really good topography data as we get gravity data, but I'm not as much of an expert on how we deploy lunar missions as we go on moonwalks. So that might not be possible. I think within a few meters would be fine, because the gravity gradient on the lunar surface is, oh, I guess maybe a few meters should be okay, to as long as it's relatively consistent and there isn't really significant gravity disturbances like right underneath the surface. It should, in general, get the bigger picture.
I think it was there and now it's gone again. So, but at least on mine it's gone again.
I see Sasha's Egan's asking, are you using P4ST?
Oh, we did that one already.
Oh, yeah.
There was a second
I stepped out.
question.
I made it myself.
And I would just.
Yeah, which I'd love to talk to Sasha more about those options too. Just to see what kind of stuff
That'll learn
we
me
get
to
into.
walk
Very good, yeah. Making sure everything was good.
Then while we do speaker transition, I will add that something that I have found useful sometimes is, I know this is horrible, using ChatGPT or some of those basic programming things.
I know.
That I can't figure out, like, how do I smooth over every other line in something?
Yeah.
So, with that coding issue, like
For sure.
generalizing the question and asking saves a lot of time.
Yes, yeah.
Granted, of course, check
Slowly-
verify.
Yes, I'm slowly getting into maybe asking ChatGPT a couple questions while I code every once in a while. I'm very hesitant.
All right, so let's thank Katie.